time complexity measures how long an algorithm takes to run as the size of the input grows. It's like saying how much time you will need to finish a task as the task gets bigger. And similarly, space complexity measures how much memory an algorithm needs as the size of the input grows. Now, in order to specify these complexities, the most commonly used notation is called the Big O notation. Big O notation is a way to describe the efficiency of an algorithm. Consider we have two positive functions, f of n and g of n. We say that f of n is big O of g of n if for some constant c and after some input n naught, g of n always grows faster than f of n. Now, this signifies the upper bound of an algorithm's runtime or space requirements as the input size grows. Now, in order for this function to be big O of n square, this condition must hold true, where c is a positive constant. Let's draw the graph considering c equals 1. Now the blue graph didn't exceed the orange one. Now let's change the value of c to 2. Now this always exceeds the orange graph. That means the function n square plus 2n plus 3 grows slower than 2n square after some input n naught. So that means that n square plus 2n plus 3 is big O of n square. But it's not only big O of n square, it's also big O of n cube or n to the power 4 or any other higher order functions. But we choose big O of n square because it's the closest upper bound and gives a more accurate measure of an algorithm's performance. Here is a quick rule to find the big O. Imagine this is the time complexity of an algorithm. To find the big O of it, first choose the most dominant term from the equation. Here it's the cube term because as the input grows, the algorithm will primarily depend on this term. Ignore all the other terms and then remove any constant coefficients from the dominant term. That's it. This gives you the big O of the algorithm. In this case, big O of n cube. Now, here are some of the most commonly used complexities, starting from the constant time to all the way up to factorial time. As the input size grows, it's clear that the factorial and exponential complexities increase much faster than the others. This makes algorithms with these complexities impractical for larger inputs, while the linear and logarithmic complexities grow much more slowly, making algorithms with these complexities highly efficient and scalable even for larger inputs. Now let's find out the big O by looking at some example codes. So this is the code for linear search. In this code we have one loop which runs through all the elements in the array once. That means this is big O of n, which runs linearly as the input grows. In the next code, we have two nested loops. For each iteration of the first loop, the second loop runs through all the elements again. So the first loop will run n times, and each time the first will run, the second will run n times. So n into n, the final complexity will be big O of n square. Now this code is a bit difficult to understand because it uses some other tools, but essentially it takes a list as an input and returns a list of lists containing all possible permutation, giving a time complexity of big O of n factorial, because the total number of permutations of a list of n elements is n factorial. And the space complexity is also big O of n factorial because it requires storing all n factorial permutations. Now let's understand what best case, average case and worst case of an algorithm are. Using linear search algorithm, best case is when the algorithm performs the minimum number of operations. For example, in this case, the best case occurs when the target element is found at the first position. Now, average case is the scenario that lies between the best and worst cases. For example, in this case, the average case would be finding the element somewhere in the middle of the list. So on average, we expect the algorithm to check half the elements in the list. And in the worst case, the algorithm performs the maximum number of operations. This happens under the least favorable condition. In this example, the worst case occurs when the target element is the last element in the list or not present at all, in which case the algorithm has to check every single element